Hello everyone, so I wanted to present something interesting about complex exponents today, and that is that if we start with Euler's famous formula, e to the I theta equals cosine theta plus I times sine of theta, we can actually manipulate this equation in many ways and get some truly fascinating results. So first, I think we should start by setting theta to being equal to the log base b of some x. So assume that this theta here, this variable, is expressible as a logarithm, in other words. So it's the log base b of some x. Well, what do we get? We end up with e to the I log base b of x, cosine of the logarithm, plus I times the sine of that same number. And so we can actually change this right side of the equation to be basically e to the I ln x divided by the ln of b, because this is actually by the change of base formula. We're changing the base of the logarithm to the natural log, and we can do that, we just need to account for it by dividing by ln of whatever the base is. And I'm going to actually abbreviate this to CIS, which is, in this case, cosine I sine. It's a bit of an abbreviation for cosine of something plus I sine of that same thing, which is really what the right side of the equation actually is. Well, we can also simplify the left side of the equation very much, and we can say, basically, it's e to the ln of x to the I, treating this I, the coefficient of this logarithm, and basically bringing it up to become an exponent, which we can do with logarithms, and it's this whole quantity to the 1 over ln of b. And that's equal to CIS of log base b of x. Now what this equals, and we can simplify this even further, this left side can be considered equal to x to the I, which is going to become very important. And if we raise both sides of this equation to the power of ln of b, we can actually cancel out this part of the exponent, and so we're getting cosine I sine of log base b of x, all of that to the ln of b. And if we, for simplicity, set b equal to e, the transcendental constant, we can simplify this even further, getting this equation, x to the I, which is a very interesting concept. You can probably see where this is going. It's basically, I'm going to say CIS of ln of x, and ln of e is just 1, so the exponent becomes 1 here. But now we actually have a formula. A very interesting formula for raising a power, or raising a number to the power I. This is very interesting. And now let us presume that x is equal to x to the I or something, or, set x equal to x to the I and just see what we get. So presume that x is expressible as some number a to the I. So we have a to the I equals cosine I sine of ln of x. But x in this case, remember, is actually a to the I. So that's interesting, and we can even move on from there and say, well, what is something to the I to the I? Well, we can actually multiply these together by one of the laws of exponents, and I times I is negative 1, so it's really a to the negative 1, or a inverse, really equal to 1 over a. And this equals I'll actually expand this out a little bit, the cosine of, well, let's think about it, ln of a to the I, this is an exponent, so we can again bring it down to be a coefficient if we want. So, why not? Let's say I times the ln of a plus I times the sine of that same quantity, I ln a. And from here we can actually substitute different values of a to be able to get some very fascinating forms. Well, for instance, if a equals 1, we get that 1 equals the cosine of I times the ln of 1. Well, what is a ln of 1? It's, most basically speaking, it's 0. Plus I times the sine of, again, we have a ln 1 factor here, and that is in this case 0. And if you, from here you can do this in your head, and verify that the cosine of 0 is 1, and the sine of 0 is 0, so this imaginary term goes away. So this verifies the equation, and it makes sense. Furthermore, however, if we substitute 2 for a, we can get 2 inverse, or 1/2, to be equal to the cosine of I times ln of 2, one of my favorite numbers, plus I times the sine of I ln 2. Now isn't this amazing? We know that this equation is true now. And in fact we can verify it with some kind of a, perhaps an advanced calculator if we wish. And it involves, as I briefly mentioned, the natural log of 2, which is approximately 0.693147. And it is, as I've said before, one of my favorite numbers. In fact, I say that in my series on the natural logarithm. And I honestly think that more people should recognize the natural logarithm of 2 as being really very, just purely interesting and important, useful kind of transcendental constant. Because that's what it is. But honestly, this equation, for x to the I, is really just purely interesting, and it's much broader than just ln 2. As you can see, I've substituted a few different values in for this equation, and what we get is really just one result of complex exponents. And you can see this table here. So if you think about it, just for fun, we can find these very fun, interesting expansions for 1/2, 1/3, 1/4, 1/5, etc. And we can actually understand, to a certain extent, why these are true. And, we can look for patterns among these cosines and sines, and what we're basically seeing, whether we realize it or not, is that when we use complex exponents, for any base, basically, we're involving cosines and sines in many dimensions. In this case, I think at least 3 dimensions, because we can see that our input is basically just 1x. It could be more general than this. For instance, we could have some kind of formula for a to the sigma plus I tau, or something. In which case we'd have, I suppose, perhaps 2 or 3 different variables for our input. But in this case, we basically are considering a somewhat simpler case, so it's x to the I. But for our output, we're actually getting 2 outputs, which is a real part and an imaginary part, and that's very interesting to consider. But anyways, thank you very much for watching, and I'll see you another time. If you have any ideas, questions, or comments, let me know.